Thank you very much to the organizers for this very nice conference. And so this is so this course is devoted to wave structure interactions, and I will do it with Geoffrey Beck. So we will have 3 parts, and we will. I will do the first lecture, and then Geoffrey. Motivation of wave structure interaction in the beginning was to study renewable offshore energies, such as offshore turbines or wave energies, where you have a structure which is floating and interacts with the wave. So there are several ways to compute this. So you could use CFD, but the computation of this is really huge. It's then the cost is comparable to constructing a prototype. And on the other hand, what is used by the engineers are models which are linear models, which are very which are not precise at all, and that do not describe the interaction of this structure with the waves in one sense. And so the idea was to use the models that have been described for the propagation of water waves. So Thomas Lazare in his course mentioned some of them, and we have been in you can see them in some posters also. You have shallow water models, Boussinesq systems, etc., that are used by oceanographers to model the waves in coastal areas. And the idea was to use this model that are quite efficient and that can be used numerically to describe the interaction with floating structure. So this is what we will describe. And so the first chapter will be to propose a general method for wave structure interaction. So it's essentially a recipe that I will implement in some simple cases, but that can be implemented in many other cases. So this is something that I proposed in a paper in 2017, and here I will consider the case of horizontal dimension d is equal to 1, just to simplify everything, but you can do it in the case of dimension horizontal equal to 2, and maybe at the end of the course we will comment on the case d equal to 2. And then I will comment on 2 different configurations of wave structures, and each of them will represent one specific difficulty, so 2 different configurations. So the first configuration is where you have a floating object. So the object is like this. It's partially immersed. I will assume that the vertical coordinate is z. What I will write, zeta, is the parametrization of the surface of the fluid. I will have a depth that for simplicity, I take constant, which is minus h0. And then you see that the waves are in contact with the object. So I will assume in this configuration that the object does not move, it's fixed, it's just partially immersed. And you see that when the waves are coming, then you have 2 contact points that I will write x minus t and x plus t. And then this is a free boundary problem. In the sense that the domain in which you cast the equation depends on the position of these 2 points, which are not given, which are parts of the unknown of the problem. Okay, so this configuration, I will write it configuration A. Okay, the object is fixed. The difficulty essentially is this free boundary problem. Then second configuration, I will take an object which is like this. So it interacts with the waves, it's the same notations otherwise. So here you see that you don't have this free boundary problem. So in this sense, it's easier because the coordinate, horizontal coordinate of the contact points are fixed. So I will write them minus L and plus L. And here the difficulty will be that I will assume that the object moves and delta will represent the vertical displacement of the object. I assume that it moves only vertically. Of course, in general, you have other degrees of freedom. For this talk, I just considered this. Okay, it's allowed to move vertically, and delta is its vertical displacement. So here, the problem will be to find delta through a coupling with the Newton's equations. Okay? So this will be configuration B. Okay? So I take these two configurations and I have one difficulty for each of them that I will comment on. So this is the first, for this recipe, if you want, the first step is to identify the configuration you have to deal with. The second step is to choose a wave model. So what does it mean? You could use several wave models to describe the free surface. So you have the water waves equations. So you have had the course by Thomas Lazare last week. And then these equations are very complicated, and in particular, we don't know at all how to solve them when you have boundaries in domain with boundaries. Okay? And then you have simpler asymptotic models. So you have, in particular, asymptotic models in shallow water. So there are some posters on this that mention this type of approximation. So you have several models. The models that are the most famous are probably the nonlinear shallow water equation, nonlinear shallow water equations. You have the Boussinesq equations. You have the Serre-Green-Nagdy equations, etc. So these models, when you go from this one to this one, essentially you have that the precision is increased. Okay. In this talk, we will focus on these two models. I will essentially do the analysis of this model and Geoffrey the analysis of the Boussinesq system. The reason of this, so we focus on nonlinear shallow water equation and the Boussinesq equation. The problem is for Serre-Green-Nagdy is that the mixed, when I say mixed, it means initial boundary value problem is open. It means that we are not able, for the moment, to prove that the Serre-Green-Nagdy equation are well posed if you, for instance, on the half line, if you impose an initial data and the boundary condition. Okay? While we are able to do this for these two equations. Okay, so what are these models? So the nonlinear shallow water equation, I can write them like this: dt zeta plus dx of q is equal to 0, and dtq plus dx of q squared over h plus gh d zeta is equal to minus h over rho dp bar. So I have to explain what these things are. So first, h is h0 plus zeta. So this is the total height of the water. So this is h. And Q is if capital U, to take the same notation as Thomas, I think, is the velocity in the fluid. Q is the integral from the bottom to the top of the horizontal component of the velocity. And this is the horizontal discharge. Okay? So you have a coupling of two equations on two quantities, zeta, the surface elevation, Q, the horizontal discharge. So this equation actually, yes. And this equation is actually an exact equation. If you remember Thomas' talk, if you take the water waves equation, you integrate the incompressibility condition from the bottom to the top, and you use the kinematic boundary condition, you find exactly this equation. So this is not an approximation. In his formulation of the equation, in the Zakharov-Krak-Sulem formulation, this equation was written dt zeta minus g zeta of c equal to 0. So if you want to make the link with Thomas' talk, this gives you an identity that can be useful, is that this can be written in terms of the Dirac-Tindalman operator g zeta k. Okay? So this is exact, and this equation is an approximation. I don't comment on the way you derive this equation, so this is well done for the water waves equation now. And also, what is P bar? P bar is equal to the pressure at the surface. So you remember Thomas' talk, he took it equal to 0. Essentially, in general, it's constant at the surface when it's in contact with the air. So in general, this term on the right-hand side disappears. Okay, and if I may do some additional remark, is that the second equation, I might use this later. The second equation can be written as dt of q over h. So q over h essentially is the average horizontal velocity. Sometimes you can call it v bar if you prefer. Plus is equal to minus 1 over rho dx of pi with pi is equal to P minus the atmospheric pressure, which is constant, plus rho g zeta plus 1/2 of rho q square over h square. And this I will call the Bernoulli pressure. Okay? So sometimes I will use this expression. This is completely equivalent. This is a simple computation. Okay, so this is the first model. I said nonlinear shallow water equation. So this is a model which is very robust, which is used a lot, which is good to describe many things, but which lacks an important effect, which is the effect of dispersion. In particular, you don't have you cannot have a solitary wave with this kind of model. If you use it to describe waves on the coast, you don't have the shoaling, which is the steepening, and when the wave gets higher when they reach the coast. So it's important to add these effects. And so actually, the Boussinesq equation integrates these dispersive terms that are neglected in the shallow water equation. So as I said, the first equation is exact, so I have no reason to change it. And the second one is a dispersive perturbation of the shallow water equation. If I don't write anything, it means dx. Okay, sorry. Okay, so this term is of dispersive nature. We can show it by looking at the dispersion relation. So this is a dispersive perturbation of the nonlinear shallow water equation. In particular, if you take H0 equal to 0 in the Boussinesq model, then you end up with the shallow water equation. So when I want to say to hold for both models, I will use the Boussinesq equation, and you take H equal to 0 to have what happens for the shallow water equation. Okay, so this is the second step of the recipe, which is you choose the degree, if you want, of precision with which you want to describe the wave. Of course, the more precise you are, the more complicated it ends up for the resulting model. Okay? So once you have made this choice, the idea is to have to see the wave structure interaction as a problem with mixed constraints. So wave structure interaction as a problem with mixed constraints. So the idea is to differentiate two regions. So what I did not write here is that I will denote by zeta w here the parametrization of the object which is immersed. So W is for weighted, okay, the weighted part of the object. And then I will differentiate the equation in what I call the interior region. So the interior region is this, which is I of t. And then I have the exterior region, which is here two half lines, E of t. I might write E plus and E minus, and E of t will be the union of the two. And here it's the same, except that here these two regions do not depend on time, they are fixed. Okay, so this is the first step. So you define, distinguish the interior region, if I write I of t, and exterior region, that I write E of t, which is, in this case, two connected components, two half lines. Okay, and there is no dependence of t in the second configuration. So, what happens in the exterior region? So, in the exterior region, what happens? You are in the standard situation. I mean, if you are in the situation of Thomas' course, where you don't have an object, and in this case, we have the surface zeta is free to move, but we have a constraint. We have a constraint on what? The constraint is on the pressure. Okay, so we have that zeta is free, but you have a constraint on the surface pressure, which is that P bar should be equal to the atmospheric pressure. Okay? And the resulting equation is that the Boussinesq equation, for instance, as I said, you take H0 is equal to 0 if you want to have the shallow water equation, becomes okay, plus gh d zeta is equal to 0. Okay, this term vanishes. And as I said, you take h0 equal to 0 to have what happens for the shallow water equation. Okay, so this is the situation which is in the, we have the standard equation, and the situation is different and actually symmetric in the interior region. So in the interior region, so this is the reverse. In the interior region, we have a constraint by definition. In the interior region, it's where the water is in contact with the object. So the surface zeta of the water should match the bottom zeta W of the object. Okay. On the other hand, the pressure P is unknown. Actually, this is one of the main unknowns of the problem, especially for this one, because this is this pressure that will make the object move. Okay, so in the interior pressure, zeta is constrained. We have zeta is equal to zeta W, but P is free. I will write P is equal to Pi. I will write an I for all the quantities that are evaluated in the interior domain. Okay, so I have no no condition on Pi at this point. So what happens to the equations? Okay, so it's in this case it's quite simple. So if I look at the first equation in the model B, for instance, or let me do it just for shallow water. Then you see that I have dt zeta W plus d of Qi is equal to 0, which is equivalent so to dQi is equal to minus delta dot. So in particular, this is 0 for the configuration A, because in the configuration A, delta remains equal to 0. The object is fixed. And so this is very easy. This is minus x delta dot plus some constant in space, but it depends on time, which I write like this, the bracket of Qi. This is the mean discharge under the object. Okay? Mean in the sense of horizontal mean. Okay, so you can solve the equation like this. And then what is the second equation? Second equation, so I remind you that it's dt Qi. So let me, I might use the second formulation that I gave here. Is equal to minus 1 over rho dx pi. Okay? So I will distinguish what happens for the two configurations. So when I am in the configuration I, what happens? I have that the object is fixed. So this is hi. So dt hi is equal to 0. So I can multiply by dt hi, and I obtain that dt Qi is equal to minus 1 over rho h hw dx pi. What I write hw is h0 plus zeta w. Okay, I have just multiplied. W. I have just multiplied this both sides by HW, and HW in this configuration does not depend on time. So this gives me this. And okay. And from this equation, so this equation is, so this is two things, an elliptic equation on the quantity pi, and on the other hand, an evolution equation on this quantity. Okay, so what is the elliptic equation? I apply dx of these two quantities, so elliptic equation. What do I obtain? I obtain that minus dx of 1 over rho hw dx of pi I is equal to dt of dxq, and dxq is minus delta dot. So it's minus delta dot dot. Okay? So it's like for the incompressible Euler equation. So you see that this equation actually is like the Euler equation, and we have a constraint. So if you want to recover the pressure, you apply the divergence. In this case, this is the one-dimensional divergence, and you obtain an equation, an elliptic equation for the pressure. Okay, so this equation has a compressible structure, and now the evolution equation for this quantity is given by this. So I will integrate this equation from x minus to x plus. So you obtain that x minus to x plus of dt qi over hw is equal to minus 1 over rho times this. And what do I mean by this? I will write this is f x plus minus f x minus, and I will have this notation, which is for the average of these two quantities. Okay? If I am in the second configuration, I replace x plus and x minus by plus or minus L. Okay, so this equation now, since the okay, and so this equation gives me an equation which is alpha x plus minus d over dt of qi is equal to minus 1 over rho times the jump of pi, where alpha x plus minus is equal to the integral from x minus to x plus of 1 over h0 plus zeta w dx. Okay, so in this case, the object is fixed, so zeta w is a non-function. This quantity only depends on the boundary x minus t and x plus t. Okay? So this is for the first configuration. So you see that you obtain an elliptic equation for P, and you obtain an evolution equation for Q. Okay. Excuse me. Here it's the object is fixed, so this is true, but in this case this is 0. Okay. Sorry for that. And for the configuration B, maybe I will not do the computation, but you obtain, the equation that you obtain is that So these are very easy computations, so I don't want to lose time with this. The idea is the same. So you exploit the structure. You have minus d. So in this case, you have that hw is equal to the equilibrium, the depth of the object when it is at the equilibrium plus the displacement delta. So this quantity depends on delta. And what we obtain is that minus d of this quantity. So now you have this second term, and you also have another one. That's important, which is this one. And you have an equation for the constant, which is alpha delta d over dt of qi plus so what is this? Alpha delta is the integral from minus L to L of 1 over h ec plus delta dx. Okay, so it's the same structure as this one. So this alpha is the same coefficient, except that now the bounds from the integral do not vary in time. They are minus L plus L. And you have a dependence in time, but from the definition of the height under the object, which is now time depending through the displacement delta. Okay, so you have this. Alpha prime is the derivative, so it's essentially minus the integral of 1 over h squared. You have a coupling between these two quantities, so delta dot, q dot, and you have this. Okay, but this is the same way to proceed as in the previous case. Okay, so now we have an elliptic equation, this evolution equation for this. So what do we need? What do we need? We need to solve the elliptic equation. So if you want to solve this elliptic equation on one interval, you need boundary conditions. Okay, so we need boundary conditions on pi I at the point x plus minus. Okay, if you have such boundary conditions, you can solve this equation. Okay, and what do you need? In this first case, well, this equation is okay. In this one, you need an equation for delta in the second configuration. The second configuration is when the object moves vertically. Okay? So if we want to obtain this boundary condition, what do we need? So this is the next step of the recipe. You need to have coupling conditions at x plus minus. Okay, so I have two domains, one in the exterior, one in the interior. I want to say they have to speak one to each other. So I need these coupling conditions. And in these two situations, the coupling conditions are different. And so I will. Okay. So what is in the configuration A? So with configuration A is this one. So everything is continuous essentially because you have that. You have continuity of Q at the contact points. So this is conservation of mass. Okay, so there is, which is something which is very natural. So you will say that Q, so Q, this is in the exterior domain, at x plus minus is equal to what? Well, it's equal to Q in the interior domain, and we have seen that in the interior domain, Q was equal to just this quantity because delta is equal to 0. So Q is equal to Qi which is equal to this function of time on D. Okay? Then you have continuity of P. So this tells you that P at x plus minus, Pi, is equal to the atmospheric pressure. Okay? I remind you that Pi is Pi minus P atmospheric plus zeta plus rho 1/2 Q square over H square. Okay, this is zeta W. So at the contact point, this term vanishes. And then you have continuity of zeta. That is that you have zeta at t plus minus t is equal to zeta W at x plus minus t. Okay? So you see that on this picture, if you look at the free surface, it's singular in the sense that you have an angle, but it's continuous. Okay, so at the contact point, you have the zeta W, which is equal to zeta. Okay, so you have three boundary conditions. Now, so you have three boundary conditions on this case. Now in configuration B, so configuration B is this one. We see that we lose some boundary conditions, so we still have continuity of Q. So in this case, it tells me that Q at plus minus L is equal. So in this case, I have another component in the interior discharge, which is depending on space, which is this one. So it's minus plus L delta dot plus this function of time. But then I lose the continuity of P and I lose the continuity of zeta. These two conditions are lost. Okay, why? Because of the discontinuity from here to here, that you have a pressure, for instance, you have at least the hydrostatic pressure of the fluid from here to here, so you have a jump in pressure. And you obviously have a jump in the surface parametrization from here to here. And of course, you cannot impose this jump. So it's different, and so we have to think a little about this fact. So for CB, second configuration, we lose two boundary conditions. Okay. On the other hand, at each contact point, at each contact point. But we have one quantity less to determine, and this quantity is because we have that x plus minus is equal to plus minus L. So this is no longer a free boundary problem. Okay, so two boundary condition less, one condition less to compute. So actually there is only one BC boundary condition. There is one boundary condition missing. So you have to add something else to the model to close the system. And what we do is that we impose conservation of the total energy. So if I write the total energy, this is the energy of the fluid plus the energy of the solid. So the energy of the fluid is the integral in the exterior domain of, so 1/2 of rho g zeta square plus 1/2 of rho q square over h square, plus the integral in the interior region of the fluid also. So this is the energy of the fluid in the exterior region. You have the same in the interior region, so it is 1/2 of rho g, the equilibrium position plus delta square, plus 1/2 of rho qi square over h plus delta square, plus the potential energy of the solid, mg delta, plus the kinetic energy of the solid, 1/2 of m delta square.
It's square over h.
Yes, thank you. Okay, so I say that I have the total energy of the system, the fluid in the exterior region, the fluid under the object, and the energy of the object. And in order to have, so this is a computation, and Geoffrey will give some detail on this, but in order to have d over dt of this total energy is equal to 0, we impose the continuity of the Bernoulli pressure. Okay, so what does it mean? It means that if it's written here, the Bernoulli pressure, so in the exterior domain, the pressure of the surface is the atmospheric pressure, so it's 0. So we need to have rho g zeta plus rho 1/2 q square over h square is equal, so I can remove the rho, well, anyway, you can remove it, is equal to pi I minus the atmospheric pressure plus rho g zeta W plus rho 1/2 of qi square over hw square. Okay? But it's simpler to write it like this. And of course, you can check that all these conditions imply the continuity of the Bernoulli pressure. Okay? If you have that P is continuous, rho is continuous, and Q is continuous, then pi is continuous. Okay? So this is the missing boundary pressure condition. And so we have everything that, that we need to solve the elliptic equation. So of course, as I said, one last thing that we are missing is in the configuration B, we need an equation for the solid. Okay? So I am at 5. So you see, you have first step, you choose your wave model, which was this. Then you see it as a problem with mixed constraints. So you express, you can solve in the interior, you want to solve the equation in the interior region. The idea is to transform the equations in the interior region as boundary or transmission condition for the equations in the exterior region. Okay, so you want to remove what happens in the interior, so you want to solve what happens in the interior. In the interior region, the equation have a compressible structure, and so you apply the techniques. So here it's very easy because it's one-dimensional, it's explicit, but you apply the techniques of the incompressible Euler equation. You obtain an elliptic equation for the pressure, as always, for incompressible Euler equation, and you also have an evolution equation for this, okay? That you could see as the equation for the vorticity. okay. And then you want to solve this elliptic equation, you need boundary conditions. This boundary condition comes from this analysis here. And the one last thing that you want to do is in the configuration B, you want to find delta. Okay? And of course, this comes from Newton's equation. So in general, in the general case, you have a system of 6 equations. You have 3 translations and 3 rotations. In this case, I just take 1 degree of freedom. So the equation for Newton is m delta dot is equal to mg plus the integral from minus L to L of 1 over rho pi I minus this. So this is the force exerted by the fluid on the solid. The minus P atmospheric is because you have the atmosphere which exerts the force from above. Okay. Okay, and then I want to use to make appear my quantity pi. So I will have that it's minus mg minus the integral from minus L to L of rho g, so zeta ek plus delta, minus minus L over L of rho over 2. So Qi in the interior region Q, we have seen that Q is equal to minus x delta dot. So I can replace Q square by x dot delta dot square divided by h ek plus delta square plus this quantity pi I, which is my Bernoulli pressure. And this is the quantity on which I have the continuity. So let's analyze this term. So, okay, so excuse me. Here, I will simplify. Actually, normally Q here you have this bracket Qi in addition. So I said it's minus x delta dot. So here, to simplify, and because we understand more or less what we should expect, is that I will consider the case of the return to equilibrium. So you take a fluid at rest, you take an object, and then you drop it. So what do you expect? The object will go in the water, then up, then oscillate like this, and you expect something like a damped oscillator. Okay? So to simplify here, we consider the return to equilibrium problem. Okay, so, which is what I explained to you. And this implies that Qi is equal to 0. Because by symmetry, you can easily see that the discharge, when you drop the object, the fluid moves in this direction and this direction. So it's an odd function. And so the average of the object is 0. Okay? So in this case, this simplifies the computation. You obtain this. And then you use Archimedes. So what Archimedes tells you that the integral from minus L to L of rho g zeta ek is equal to rho zeta ek is equal to m, to minus m actually. So this is a negative quantity. Zeta is under the axis z is equal to 0. And this is the volume of the water displaced by the object, so it's equal to its mass. Okay? So this term here simplifies with this one. Okay? So I just want to comment on an important effect here. Okay. So Okay, and so what do I obtain? I obtain like minus m delta dot. I have this term here, which is linear in delta, that I put on the left-hand side. Oh, no, doesn't matter. So it's equal to 2L 2L rho G delta. Okay, so this is the term which is together with the first expression here. And then this is equal, it's a plus or minus, I don't know. So let me write it like this. Okay. Is equal to minus rho. Okay, let me call it n delta, a function of delta, which is of no importance here. It's a nonlinear term. What is important is that I will consider the last pressure term. And for the last pressure term, I will write it like this, plus I will integrate by parts x 1 over rho dx pi plus 1 over rho okay, so I have just integrated by part in the expression integral of pi. I say that it's the integral of minus x d pi plus the boundary term. Okay, so this is just an integration by part from the previous term. Okay, but then where I hope I have not erased it. Where is it? Maybe somewhere. Yes, it's here. Okay. Why did I do that? Because I have already an expression for dx pi. So, but we know that 1 over rho dx pi I is equal to dt of qi over h. Okay. Is this, and in this case, we know that it's dt of minus x delta dot over hw plus delta. Okay, so you can replace in this expression, and moreover, you have that x pi I like this is equal to x of pi. So this is the continuity of this Bernoulli pressure that we have used. And now, since at the two boundaries x is equal to L or minus L, this is equal to 2L times the average of pi. Okay? And so you see that this term is very important. And this is why I make these computations, because this is something that you will have in all fluid structure interaction problems. And if you don't have it in your equation, you have to understand why you don't have it. Okay? It means that it has been neglected for some reasons. But otherwise, it can mean that you have missed something. So it's really important that in the pressure, when you have this wave structure interaction, you have always in the pressure a term which is a second order derivative of the equation for the solid. You see that this is a term in delta dot dot. Okay? And if I compute it, I find that minus x 1 over rho dx pi I, actually this is minus the integral of x square over hx plus delta times delta dot plus x square this term is not important. This term is important, and in particular, this is positive. In this case, strictly. And this quantity is called the added mass. And it's very important that you do this analysis, because then, in the end, you can rewrite the equations. So in the end, there's some small computation, but not difficult at all. That you can rewrite the equation as m plus the integral of x squared over hx plus delta. So delta dot dot plus 2L rho g delta plus a nonlinear function times delta square is equal to minus 2L over rho times the average of pi. And if you want, this is rho. Okay, if you prefer, you can write it as minus 2L, the average of g zeta plus 1/2 of q square h square. So this quantity, as I said, MA, which depends on times for delta, is called the added mass. So what does it mean? It means that when an object moves, so of course it has to accelerate itself. So in Newton's equation, you have this m delta dot, but it also has to accelerate the fluid which is around itself. So it's like if it had more mass than its actual mass. And so you really have to put it there, because of course, if you don't do this, you have this term on the right hand side, but then you can have theorems, you can have do numerical simulation, etc. But you will have some smallest condition of some instability in the numerical side that will appear, and that are completely artificial, because this term is a leading order term and should be treated like this. Okay, so this is, I think, an important message. If you do wave structure interaction, look at the added mass, and okay, and be sure of where it is. Okay, it should be on the left hand side. Okay, and then what comments can we do on this? Other comments can we do on this equation? So the comments. As I said, there is this added mass, which is an important point. There is this oscillator structure. So I would put it like this, but you recognize it. So you have this nonlinear term in addition, but otherwise you see that you have an equation of the form delta dot dot plus constant delta. So you have the frequency of this operator. You can see that on what it depends, at first order on the mass and on the size of the object. Okay, so you can compute the frequency of this operator. Then, of course, it's modified by a nonlinear term, and more importantly, it's forced, interacts, if you want, with the exterior fluid. Because you have the forcing term through the forcing term average of pi. These quantities are the traces, zeta and q are the traces of zeta and q in the exterior domain at the point plus minus L. Okay, so this oscillator will be forced by the wave that comes from the fluid, and on the other hand, it will send wave to the fluid. and this is this other comment, is that, as I said, we expect a damping. So here we don't have vertical damping term, but we have, it's another kind, if you want, of implicit damping. It's not the Landau damping, but the way the damping is observed for this is that the object, when it falls, it creates waves, and the waves, they go to infinity. So the energy of the waves has been transferred by the solid, and so the solid is damped because of the energy it sends to the wave. And so implicit damping by transferring energy to the waves. Okay, but of course, the reverse mechanism can occur. I mean that if you have an object which is at rest initially and that the waves are coming, then by this term, the same term, the object will start moving. Okay, so you have this coupling in both directions. So this is a two-way coupling, two ways coupling with the fluid. Okay, and so now we are set. We can reformulate the problem as a simple mathematical problem, which is a transmission problem only on the exterior domain of the field, where you have your standard equations. The only trace of what happens in the interior of the coupling with the object will be in the transmission conditions. Okay, so this is the last step, formulation as a transmission problem. Okay, so I think I will differentiate the two configurations to be easier. Okay. So configuration A and configuration B. Config A and here config B. I have, as I said, the standard equation. So I write them for, okay, shallow water I said. So the standard equation, always the same. Okay, and then it's in minus infinity x minus t cup plus t plus infinity. So in the exterior domain, I have two connected components. And so I want to see this. I have transmission conditions. So what are the transmission conditions? So we have seen that Q is continuous at the boundary point, and that under the object, in this case, the object is fixed. So Q is equal to minus to bracket of Qi. So it means that the jump of Q is equal to 0, and that you have the bracket of Q is equal to the bracket of Qi. So we have a transmission condition like this, and so we have a condition on the average of Q, and this condition takes the form of an ODE, which is alpha of x plus minus t of d over dt of qi is equal to minus 1 over rho. So I will write it like this. Okay, so this quantity qi that you use as a transmission condition, you have to determine it by an ODE, which is forced by the solution of this. Okay? So what does it mean? It means that if you want to solve this problem, you need to know the boundary condition. But if you want to determine the boundary condition, you need to know the solution of this. Okay? So which means that this is coupling in the two sets. And the problem is not finished here because I don't know x plus minus t. So we need an evolution equation for x plus minus t. And this is the last boundary condition that I did not use so far, is that zeta of t x plus minus t is equal to zeta w of x plus minus t. So you have an implicit evolution equation for x plus minus t. Okay? Because zeta w is a non-function, it is fixed, and you have this condition. So this is a strange boundary condition in the sense that, contrary to all the boundary conditions that we have seen so far, in, for instance, in Thomas talk, or, this boundary condition is not kinematic. When you have the case, for instance, of vacuum, or in the case of the shallow water, it means that you have the shoreline. So the depth vanishes, and in this case, the motion of the contact point moves with the velocity of the fluid. You have x dot is equal to u, the velocity of the fluid. Okay? So a point which is at the contact line remains at the contact line. In this case, this is not true. You can have, when you make the object, the contact point with the object, a particle which is at the contact point does not remain necessarily at the contact point. And the problem of this, a consequence of this, is that if you make a Lagrangian change of variable, you don't fix the boundary, okay? Which is a bit, which is not convenient because in many cases it's convenient to work with Lagrangian variables. So this is, I will comment on this later, but this is a non-standard boundary condition. Okay, in configuration B, so we have the same equation, but now in a domain which is fixed. Okay, so no free boundary condition. And now we have transmission conditions also. Which is the following. So the jump of Q. So now, because the object moves, I have the Q under the object is minus x delta dot plus this average of Qi. So I have minus 2L delta dot. And here I have Q is equal to Qi of t. And then, of course, I need boundary conditions on an equation for this one. So I have alpha delta d over dt, the same essentially as before, which is coupled, as we have seen, with the equation for delta is equal to minus g zeta plus 1/2 of q square over h square. And here you have the Newton's equation, which is m plus ma of delta dot dot plus 2L rho g delta plus this nonlinear function that I don't write is equal to minus 2L over rho times the average of the same quantity. So it's a bit, so you have now two non-homogeneous transmission conditions, each of them being solved by an ODE, so it's a system of coupled ODE, which is forced by the traces of the solution in the exterior region. Okay, but this is a free boundary problem. This is not a free boundary problem. So of course, this one is easier to handle mathematically than this one. And then, okay, so I will now comment on the mathematical analysis of such a transmission problem. Okay, but okay, so this is the important point is that we have reduced the whole problem to a simple transmission problem in the exterior domain, and with transmission data that are found by solving an ODE which is forced by the trace of the solution in the exterior domain. Yeah? And so the coupling acts in both ways. And you see also that a mathematical problem we will have is that we will have to control the regularity of the trace of the solution. Okay. So this will be an important point of the analysis. So this is okay for this first part, which is a derivation of the model. So I did it in two simple cases in 1D. So if I have time, I will comment on the two-dimensional case, which is a bit more involved. Here it's very simple. And now the problem is to analyze this transmission problem. So what I propose is to make to give you some basic things about, since the course on the analysis of initial boundary value problem for hyperbolic systems. So this is a case of the shallow water equation are an example of nonlinear hyperbolic system. So I will show you how you control the, so you can analyze in 1D the initial boundary value problem for such systems. And then Geoffrey will show when you add a dispersive term, a dispersive perturbation, when you look at the problem in the whole space, as soon as you don't go to the, you stay before the times where the shocks appears, the perturbation remains a perturbation. The analysis is, the dispersionless limit is trivial. When you add the boundary, it changes completely the analysis. So, so before doing this, I will give you the basic points for the analysis of the hyperbolic case. Maybe if you have question on this modeling part, or I can start with the second chapter. Okay, so this is chapter 2. So we can forget about all this because I will now start with an abstract setting and give you the main important points when you have to analyze this kind of problems. So, chapter 2. Initial boundary value problems for hyperbolic system in dimension d equal to 1. Because dimension d equal to 1, there are many things that can be done quite simply, just linear algebra, while in dimension higher it's more involved. And here we are in the one-dimensional case. So the linear problem so I will consider dtu plus a of tx dxu is equal to f for t positive and x positive. I will consider a boundary condition n of u is equal to g. So it's t positive and x equal to 0. And an initial boundary condition, which is u at t equal to 0 is equal to some function un of x, so it's t here. So for x positive. So u is a function of time times and space, and which takes in value in Rn. A is an n by n matrix, and n is a p by n matrix. So p is the number of boundary condition of linear boundary condition that you impose. P is the number of boundary condition. So first, you might say, okay, but you're speaking about boundary value problem, and what we have to deal with is a transmission problem. So first, let me mention that a transmission problem is an initial boundary value problem. Okay, so for instance, let me consider this system, for instance, and you will understand easily how to generalize it. Take okay, no. Okay. I take x equal to 0, and I take a system here which is dt u left plus a left dx u left equal f left, and I take another hyperbolic system here, okay, and at across x equal to 0, I impose some transmission condition which are n, how can I write this? N of ul ur is equal to some function g. Okay. Then, if you want to transform this into an initial boundary value problem, so this is very easy. You say that u tilde L is of Tx is equal to ul of T minus x, and you do the same. You do the same for all the other quantities, and then you obtain that dt of u tilde L ur plus minus a tilde L ar dx of u tilde L ur is equal to f tilde L fr. Okay, and n u tilde L ur is equal to g. Okay, so this is on x equal to 0. So this is so you can see that an n by n transmission problem is actually a 2n by 2n initial boundary value problem. Okay, so I can speak about initial boundary value problems without loss of generality. Okay, so now, maybe reminder. Wait. No, I'm. Okay. Reminder on the case without a boundary. So essentially, this is something that Elena did last week on the case of the equation, but the analysis is the same. So here I forgot about the boundary. I consider the problem on the full line. So dtu plus a tx dx of u is equal to 0 for x in the full line, and I take u at t equal to 0 is equal to un. So this is just the Cauchy problem. Okay, so I want to keep my notations. Okay, so so I want to have energy estimates for this. So I will use this assumption. So on the matrix A, I will assume that it's Friedrichs symmetrizable. So we have a Friedrichs symmetrizer. What does it mean? It means that there exists a matrix S, symmetric definite positive, such that you have two constants, alpha 0 and beta 0. Okay, so this is just the coercivity of the matrix. And second, you have a constant beta 1 is at V times dTs, so it's the time space divergence of the matrix. V is smaller than B1 V square. Okay, and what I want to prove is that if, this is a priori estimate, so if U is a regular solution, then we obtain that the sup in time, say exponential minus lambda t times U is smaller than the constant in L2 plus, so if I do the simplest case, I will take the L1 norm. Okay, the standard L2 estimate. And so this is a very standard computation. I multiply. F is a forcing term. Excuse me. F, and of course, if the assumption is satisfied, okay. And so I have just 2 minutes to end this. So it's just to remark that you have ds u dot u. Okay, so you have, if you differentiate dx, you have the dx that can go on this quantity and can go on the u. But since SA is symmetric, if the dx goes here or here, it's the same. So this gives me this component. Okay, so I use the fact that because SA is symmetric. And therefore, if I look at the quantity d over dt of exponential minus t su u, I find that it's 2 lambda exponential minus 2 lambda t su u. So this is, if the dt hits this exponential, this kills me this one. Okay. And on the right-hand side, I have 2 exponential minus 2 lambda t sf u plus minus 2 lambda t dts plus d of SA of u. Okay, I'm sorry, I forgot. And this is for lambda larger than beta 1 over alpha 0. And there is a smallest condition on lambda has to be large enough. And so then this is done. Okay. Why is this done? Is because this controls alpha 0 u square. Okay. And this is absorbed by alpha 0 u square if lambda is larger than beta 1 over alpha 0. And beta 1 is the control this one. So you can control this by this, and then it's just integrating. Okay? So, okay. I just wanted to remind this energy estimate and to comment, because I will use it, and it will be, of course, different in the case with a boundary, because this integral, when you integrate this, this is 0. Okay. When you have a boundary, this is no longer 0. Okay. Okay, so I will stop here, and I will follow this analysis of hyperbolic systems in the next course. So thank you.